So I'm going to talk very briefly here about optimizing models with pre-processing and variable selection, but I'm really not going to do any of it because we don't have a lot of time. So what is pre-processing all about? Sometimes I actually say that the secret of eigenvector research is pre-processing. Um, Pre-processing includes any procedure done to transform data before you model it with PCA, PLS, whatever, curve resolution neural networks. Pre-processing is often the critical difference between adequate and inadequate models. So often it's what you do before. I mean, basically everybody's PLS is the same. The what the differences are in what you do before that. So there are a lot of ways to pre-process data. Many of them are particular to spectroscopy and spectrometry. The goal of pre-processing in general is to remove or reduce variation that you don't care about and emphasize variation that you do care about. So you don't care about variance that's not related to the problem you're trying to solve. So in our case, variation that's not related to the concentration of glucose. Uh, and there's a lot of possible sources of other variation. We do care about the variation that's related to, in our case, the glucose. Um, So pre-processing then lets the analysis focuses on the variation due to your problem of interest. So sources of variation that's not related to your problem of interest, well, measurement noise, baseline effects. We saw that in at least one sample in our data set. Nonlinearities from the detector or sample matrix effects. Of course, the presence of other analytes that we don't care about will add variation to a data set. And then physical effects such as light scattering and sample temperature or pressure variations. We're generally looking for the chemistry, not the physics here. Intra-class variation, variation within, that's more of a classification thing. Um, our variation of interest is really the signal from the analytes or property of interest. If we were doing a classification problem, we're just really most interested in the between class variation, and that is the variation that separates classes apart from each other. And we sometimes call all these things right here clutter. And let me turn my pen back on. So uh, these things we refer to as clutter, and that is the things that clutter up your signal, so to speak. That terminology actually comes from the early days of radar when they said they got clutter on their radar screen due to effects like flocks of geese. So a couple of things that we do to try to improve the clutter situation and reduce nuisance variance are background and baseline subtraction. That's removal of broad low frequency interferences which retain higher frequency features. Uh, you can detrend spectra. You can do selected points baselining. We have some routines like weighted least squares baselining that automatically fits uh, points to the bottom of a spectra and then subtracts the baseline out. There are windowed methods like Whittaker and rolling ball. So there's a lot of ways to do baseline subtraction. In some instances, you might want to do sample normalization. Now, normally you don't do much normalization when you're doing a quantitative problem. Normalization is a little more common in classification problems, except for multiplicative scatter correction is a real common normalization method where you determine a scale factor that best fits a new spectrum to the reference spectrum. And that is used in quantitative models quite a little bit. It is technically a normalization method. One of the problems with normalization methods is that they can blow up noisy samples to have more variance, so be aware of that. And we also, of course, use smoothing and derivatives. Uh, the uh, general idea here is that if we have an original spectrum, this blue here one, and let's add to that a baseline offset and create the red one, and then add to that also a sloping baseline and get the green one. Well, derivatives can make that go away. What we do is we do the derivative of the absorbance here with respect to wavelength. And there's a method called Savitsky-Golay. It basically fits a piecewise polynomial to each spectrum and can do a derivative of it. Turns out you can boil all that actually down to a set of coefficients that you just multiply the spectra by, and that was the main gist of this. The Savitsky-Golay original paper is this showing how to boil it down to the coefficients. If you do a first derivative, it'll remove an offset, so that'll make the red one fall back down on the blue one. And a second derivative will remove an offset and a slope, and that'll make the green one fall back down on the blue one. Another thing that we're fans of is orthogonalization filters. And if you're going to use an orthogonalization filter, the first thing you need to do is develop a description of the clutter. And that is, you need an example of the variation that you want to eliminate. So that's a variation in samples that are not related to the analyte of interest. Uh, Use that description then to develop a filter to remove that variation, to remove that clutter. A couple of common ways to do that: external parameter orthogonalization. You use PCA of the clutter variation to develop a basis for the variation, and then you filter that data out. Essentially what you do is you then your filtered data is the residuals on a PCA model of the clutter. And we also use generalized least squares weighting a lot. That's actually the inverse square root of the clutter covariance. So I'm not going to go into detail on that. It gets a little complicated, but the general idea is you're going to try to shrink the dimensions that the clutter is spreading around. And of course, it's also possible to improve models through variable selection. Irrelevant and noisy variables degrade a model's performance. There's a lot of methods available to select the best variables. And I put best there in quotes because, yeah, you're never going to find the best. The problem being that if you have over a few hundred variables, the number of possible selections of variables within that is a very, very large number. I mean, you get into numbers real fast that if you could evaluate one selection per second, it would take you the age of the universe to complete all possible combinations. And so, you're not going to do that. So you're never going to actually find the best, but you can find a better set than what you've started with. So methods to do that include stepwise, forward or backwards, interval PLS, looking at the loadings plots and using the variable influence on prediction to select what variables to use, or the selectivity ratio. You can do it with genetic algorithms. Um, and there are many, many others. The ones that I've listed are ones that we actually support, but there's a lot of other ones out there. So all those things can be done to improve the model. And of course, what did we do? One of the things that we did was we just looked at the spectra and chose it by hand. So we did some variable selection by inspecting the loadings and using just the areas that we thought the information was in. So that was variable selection.
I had a question about removing a known interferent from a spectra
Right?
before you model.
Yeah, the problem with that tends to be you have to do it exactly right. And um, if you don't, it just messes things up. So it's usually better. to let the model handle it than it is to try to subtract it out beforehand. I've seen too many instances in the past of where people try to do that. And, oh, okay, so if it works perfectly, what should happen is it should decrease the rank of the data by one for each thing that you've gotten rid of. And you'll know it's not working if that doesn't happen. And I've seen too many instances of people trying to do that where they actually increase the rank of the data because it wasn't done exactly right. So, it's possible if you can do it perfect, but if you can't, let the model handle it. And um, you might be able to build a filter for it instead, uh, and that would be a softer way to do that that's less prone to screwing up, so to speak.
Great, thanks.
Sure. Anything else, Scott?
Um, we got a lot of questions going on in the chat, and we're covering most of them in the chat. Um, but if we get towards the end here and you have a question that didn't get addressed, please repost it, and we'll try to get it.
Okay. Uh, good. So all these combinations of pre-processing and variable selection can lead to a lot of different combinations of models. And what I'm showing here is a screenshot out of our model optimizer tool that can actually help you first create all these combinations of models with different pre-processings and variable selections, and then evaluate them. And that, of course, is would take a while to go through. So I'll just note here that it exists, and I'm going to send you to some other resources on that. Uh, Conclusions: models can often be improved by optimizing the pre-processing and the variable selection. I'll warn you, though, it's generally easier to make a good model better than to make a bad model good. And uh, variable selection, especially if you don't have something that kind of works to begin with, variable selection usually isn't going to help you, which is a bummer because it feels like it fails when you need it the most. But that that's just life. PLS is pretty good at finding relevant information. So if the model isn't at least kind of working to begin with, you probably can't save it. It does lead to many possible models to sort through doing these things. So some pre-processing and variable selection resources. Here's some webinars, everything you need to know about pre-processing and everything you need to know about the model optimizer. I did a talk recently that I recorded on final model selection, on how do you select models out of this whole smorgasbords of ones that you might wind up with. And so you can find that at the link there on Vimeo. And of course, we teach classes at our Eigenvector University, and we have them recorded also in advanced preprocessing and in variable selection. Okay. And I was going to show a bit about, I will do just a little bit here on preprocessing. So let me just go back to our MATLAB. So it's easy enough to change preprocessing into more advanced methods. And what I do here in the interface is if I click on the P, I can say edit preprocessing. And if I open that up, I get all of these possible preprocessing methods right here. And so I can actually add those. Right now, all I'm using is mean centering. So this is what I'm using. This is all the things I could use. So for instance, we could try easy enough a derivative and see what happens. I can select derivative, say add. These are the parameters in the derivative. I'm just going to use the default settings of a window width of 15, polynomial in order 2, and first derivative, and say OK. And so now my selected methods are first derivative followed by mean centering. And I'll say, okay, that's all right. Okay, there we go. And I can remake this model. And I can see right away that didn't help uh, in the model because my error was down around 0.08. Now I'm up here around 0.15. It doesn't seem to get better with more factors in the model. So that didn't help. One thing that is sort of funny in here is you'll notice that in our uh, measured versus predicted, it actually moved some of our bad samples, though, closer to the line, especially this one, because that was part of the problem with these samples was their baseline offset. So it didn't improve the model overall, but it actually improved its performance on these outlier samples. Another thing that you could do is you could enable the clutter filter here. So I'm actually going to just move us back to mean centering, but then also open up the clutter, and I could use those classes that I set up in my data set and make a filter on them. Now, why could I do that? Well, think about this. Each one of those classes is at the same concentration. So all the variation within it is variation you don't want to see. You want each concentration to be the same. And anything that makes those look different isn't due to changes in glucose, it's due to other stuff. So I could do a GLSW filter on that uh, and make a model out of that and use it and go ahead and calculate that. And that gets us to about the same model that we had before. It's not actually quite as good as that one. We're at about 0.94 here on our error cross validation. Our other one was down around 0.08 something. So that was another possibility. It turns out that in this data set, after having gone through quite a few things, about the best model that I could find here is a plain vanilla PLS model with mean centering and just using that selection of variables that we did, kind of throwing out the areas that didn't seem to have any signal in them. And so that is about the optimal model here. I'm going to just go back to mean centering, then reset it, make the model, and go on with the presentation.
Yeah, we had a couple of questions, and I think it's sort of like how do you find that balance where you're adjusting your pre-processing, you're trying to figure out did I improve things, did I overfit, like what's the general guidelines about those little iterations as we're building up a model?
Yeah, anymore, my approach to that is build them all and look at the ratio of cross-validation to calibration error versus error cross validation, because that'll show you really quickly what models are overfit, which ones have the best cross-validation error, and if you also then highlight ones of different uh, pre-processings or variable selections, it'll tell you a lot about what's working and what isn't in general. So anymore, if I have to do a model, I use the model optimizer and create all possible combinations. Sometimes I wind up with 500 or 1,000 models and just tell it to calculate them all, look at that plot to find some candidates, and then whittle it down from there. It's uh, I I guess I've gotten a little more brute force about it over the years rather than trying to pick through them all by hand. I use the tools to look at a lot of them simultaneously. This one though, in a world where models look like this one's pretty easy. I can do this one by hand, pretty simple. One that has thousands of samples with lots of different variations in the data, that's going to be different. Okay. I don't know how satisfying that was. Uh, saving and documenting models. Saving a model, we just go from the file menu and say save model, and it'll come up with a name for the model, PLS model, and give it a date and time stamp. And so you can call it that, or you can call it something that you like glucose model. And so here, if you save that with glucose model, it'll show up in your workspace with this icon here as a model, and it'll say that it's a PLS model right over here. And then, of course, you'll want to save that back out to your workspace if you want to keep a permanent copy of that. Models actually get saved in the model cache, um, but they're you have to be a bit careful there if you're making a lot of models. Your cache gets purged every once in a while. So anything that you want to save forever, you really want out to save out as a mat file. Also, there's model details. If you want to know more about your model, if you go up to the tools menu and say show details of the model, you'll get this window up right here. And I wanted to point out that this has all the information in here about what was included in the development of this model. So here, this says what samples are included. This is what variables were included in here. And it also shows you the variables that are included. This is just their index number. This is actually their Raman shift right here. And so that shows you what's in it, how it was pre-processed, and then all the statistics of the model and its variance captured. So that's something that you probably want to save that file in order to document your model. And then there's also the report writer, which again, here under the tools menu, if you go to the report writer and select one of these three. Now on a Mac, I only have the choice of HTML. If you're on a PC, you can save your model report as a PowerPoint or Word file directly. And that'll report will include the model details, copies of all open figure windows associated with a model, and auto-generated preset plots. I think I'll actually just show that to you. So here, let's see. Um, So I'm going to do this. I'm going to say view excluded data. I'm going to turn that off. So my plots will look a little better right there. I had this plot up. I had this one here. And so now if I go to tools menu and I say report writer, HTML, I can put a comment in here for class and say, okay, auto generate standard plots. I'm going to actually say no, and that'll just make the a report out of the ones that I have up on the screen. And so it's going through and saving copies of these. And now it's starting up my web browser, and here's the report. So this is now just popped up in my web browser. This is the model data files, the sum of squared captured, and all the figures that I had open when I made the model or made the report. So I can save this now, and all these figures are available as both EPS and FIG files. And if I was on a PC, I could have pushed all this information into a PowerPoint or a Word file. So that is a really easy way to do an important task, which is documenting your model. Okay. Just a couple of resources there. There's a couple things on the wiki that you might look at, loading and saving, and the report writer. So before we finish this, I wanted to say just a little bit about model maintenance. And that's kind of the last item in the full chain of events, from starting to take data to making a model to getting that model online. You also have to consider how you're going to maintain that model. Well, why do you have to do model maintenance? The model itself, of course, doesn't change, but numerous things can cause calibration models to become invalid and to produce poor predictions or classifications. It can happen that your samples move to a range outside the original calibration, and it can be that your analyte or interferent goes beyond the calibration range or occurs in some unusual combination you hadn't seen before. There could be a new variation introduced into the samples, uh, like a new variation in a physical parameter like temperature that you hadn't seen before. There can be a change in the sample matrix that causes the relationship between the analyte and the measurement to change. It can be a change in pH, a change in particle size distribution. And of course, there can also be changes in the hardware, and the hardware has gotten a lot better than it used to be. I saw a piece on a manufacturer's website looking at their Raman instrument. In fact, it's this one that we use for this data set, over a long time, and they're much more stable than they used to be. Um, but still, you can get changes in the fiber optic due to aging of the fiber optics, changes in the source, a lot of things that can happen. So before your model goes online, develop a plan for its maintenance. We've seen too many instances of models that were making a lot of money for people that then stopped making money for people, and they had no money in their budget to update them to keep them working right. So, plan on this at the beginning. Put it in the budget. Also, it's really useful to measure standard samples on those. Plan for registration or amplitude shifts. Characterize your instrument in the ranges important to the model. And this was my model maintenance roadmap that I developed some years ago. And I won't go through the whole thing, but there is quite a few steps and questions that you can ask yourself about what is making models go wrong, and then there are different things that you can do in order to fix them. And it's probably no surprise that we offer a course on model maintenance. So here are some resources for model maintenance. There is a webinar, everything you need to know about how to build and deploy instrument standardization models, and another one, how to embed instrument standardization models into multivariate models. We have an Eigenvector University course, of course, and Bob and I wrote an article a while back, Model Maintenance, the Unrecognized Cost in PAT and QBD, and you could refer to that. Okay, so we're at the overall conclusions phase of this. There's just a few takeaway messages I hope you got out of this. One is that good calibration models start with good planning. Recognize your sources of variation that you're going to have to incorporate into your model that it's going to have to deal with. Do an experimental design or representative sample selection. And again, experimental design might not mean that you go use some experimental design software. It might mean that you use your brain and a pencil and a piece of paper to figure out what variations you need to put in. It's really not that complex most of the time, but you do have to think about it. So once you've done your design and measured your samples, review and screen your data, try to do it as the data is coming in. Use plotting and PCA, find outliers, identify trends and causes in of the trends in the models or in the data to the extent that you can. And then develop your regression model. That's an iterative process. It might take you a while. And this is one of those things that people sometimes think they're going to do that in an hour, and they might have spent weeks or months collecting the data that it's based on, and uh, think they're going to make a model in an hour. And that's usually not how it works. And of course, if it's a model of very high value, it might be worth spending a few days on. This is not at all uncommon for ones that are really important. And optimize the model. There's a lot of pre-processing methods available to handle various problems in the data, various variations that you see that you want to ignore. You can also do variable selection, evaluate the choices. You typically wind up with a lot of choices, and we provided some resources there as to how to choose. Save and document the model. You'll almost always need to have some documentation as to what was done. That could be a lot of help when you have to redo the model later and update it. Get it online. There's a variety of methods available. The selected method, for instance, whether you use model exporter or solo predictor, depends on the infrastructure you're trying to integrate with, or whether you're just going to use that model in the laboratory and can just do it in PLS Toolbox or Solo directly by loading new data into it. Depends on how it's going to be used. And plan for model maintenance. Models don't last forever, or at least I should say that the data streams that come in do not stay the same forever. So with that, I'd like to thank you for attending. I've really enjoyed developing this class and giving it. And do we have any more questions, Scott?
Not right now, but we did get
Everybody's
a
just
lot of
worn out.
yeah, I had a lot of questions in the chat today for sure.
Mm-hmm.
Um, yes, we will have these videos up hopefully today. I will put that on my to-do list.
Okay. All right. Well, if there's nothing else, I'd kind of like to have some breakfast. Oh, so there's a question about what is the correct order of pre-processing? Okay. So there are definitely a couple of rules of thumb there. Um, One is that almost always a step that includes mean centering ought to be last. So usually mean centering is or auto scaling is last in the process. And there are some things that don't work correctly, like you need to do a multiplicative scatter correction before you take a derivative. If you try that the other way around, it just won't work. In general, though, there's a lot of pre-processing methods that don't matter what order they're in. Uh, a lot of pre-processing methods can be cast as affine transforms. And if that's true, then it doesn't matter what order they're in. Um, there's a caveat on there. It depends on where the parameters that govern them actually come from. So one of my suggestions is use the plot preprocessed data function and look at it and see what it looks like. And I really suggest that if you have a number of pre-processing methods that you're going to use together, look at your data after you've applied the first one, then the second one, then the third one as you add them. And you'll see if you go awry. Also, use color by to plot your spectra colored by the analyte of interest, and we showed examples of that. And that'll also tell you whether your pre-processing is doing what you think it's doing. Other questions?
Uh, is there a white paper um, that has talks about pre-processing order and provides suggestions?
We got a course.
So, yeah, we do. For model maintenance, is it possible to track which data set is used for modeling and validation and who and when it is built? or who and when it was built. Yeah, that information is kept both in the model and in the data set. We have a history field in the data set that keeps track of who created it and what changes were made to it. Um, and then our models also have uh, information about the date it was created and last modified and who created it.
Anything else interesting?
I think it's starting to wind down a little bit.
Okay.
Thanks, everybody.
Yeah, thank you. Thank you, Bob. Thank you, Scott. Thank you to the rest of the Eigen guys for covering questions in the chat. It looks like it was pretty busy. And with that, I'm gonna stop recording and sign off.